Alright, so in Chapter 2 we are being introduced to our current model of the atom, or a simple working model of the atom that we call the Rutherford model of the atom, or sometimes Rutherford's nuclear model of the atom. And the development of this model was really described in the early parts of Chapter 2, and you should be familiar with the contributions of people like J.J. Thomson and Robert Millikan, and of course of Ernest Rutherford himself. Okay. Now, in this model, there were identified in the early 20th century that atoms consisted of three subatomic particles. We have the electron, the proton, and the neutron. So the electron is a very tiny particle contained within all atoms that has a net negative charge, and we give it a relative charge of -1. The proton is a positively charged particle, which is much more massive, around 1800 times more massive than an electron, and it carries a positive charge. And we say the proton is a +1 charge and the electron is a -1 charge. Okay? There is also another particle that we call the neutron. It has no net charge, and it's about the same size as a proton, a little bit bigger, but again, what's important is that both the proton and the neutron are very large, whereas the electron is very small in size. Now, the structure of the atom is really what allows us to understand the nature of atoms, and in particular, of course, the chemical nature, what makes one atom behave chemically the way it does, as well as its physical behaviors. So Rutherford's model is called the nuclear model because essentially it contains a nucleus. So all atoms contain a very tiny, dense nucleus that carries a net positive charge. It has a positive charge because it contains those positively charged protons here. So it has positively charged protons, and most atoms also contain neutrons. And again, remember that these particles were much more massive than were the electrons, and essentially all of the mass of the atom is contained within this very tiny nucleus, again, which carries a net positive charge. Well, the positive charge of the nucleus is balanced by the negative charge of the electrons, and so the electrons move around this very tiny nucleus, occupying the space that surrounds the nucleus of all atoms. And so really, if we look at an atom, if we were able to see one, which is really quite impossible, but most of the mass is in the nucleus, and the rest of the atom is occupied by a limited number of these very tiny electrons. And so really, the most of the volume of all atoms is in fact empty space. And when we look at this model, the structure really gives us some insight into the nature of chemistry. That is, we see that these electrons are on the outside of all of the atoms. They occupy that volume on the outside. And this is significant because this suggests to us that these electrons are what are important for the chemical properties of all elements. And this will be a common theme throughout our understanding of the structure of atoms. Now, another important feature of this model is that it really defines why atoms are different. So, for example, all atoms, including hydrogen and carbon, contain a dense nucleus and surrounding electrons. However, all hydrogen atoms always have a single proton in the nucleus, and so this number of protons really defines what type of element. Anytime there is one proton in the nucleus, we are certainly dealing with hydrogen. If there are 6 protons in the nucleus, as there are in carbon, then we are dealing with a carbon atom. And there are no other atoms that have 6 protons in the nucleus other than carbon atoms. And so we define what we call the atomic number. This number can be found in the upper portion of the box for each element. And so hydrogen has an atomic number of 1, telling us that there is 1 proton. Carbon has an atomic number of 6 and therefore has 6 protons. If we were down to pick this box right here, which I believe is zinc. They tell us that there are 30 protons in zinc because its atomic number is 30. Okay, so the atomic number defines the number of protons, and it also defines really what element we're dealing with. Now, importantly, in neutral elements, in neutral atoms, I should say, neutral atoms, that is, those that do not carry a net charge, i.e. not ions, okay, the number of protons, which is of course given by that atomic number, is always equal to the number of electrons. And as we had said, it's the electrons that are important for the chemistry. And we'll find that it is the structure and the arrangement of those electrons within atoms that really determines the chemical properties. So the atomic number gives us the number of protons, which in a neutral atom also gives us the number of electrons. And we can also figure out the number of electrons present in ions, but we'll cover that at a later short. Okay, in our next short, we're going to now talk about isotopes.